Constanzo. I'm a postdoctoral fellow in Sherbrooke University, supervised by Benoit Paquet, and today I will interview Olivia Kelada. Sorry. My subject, my scientific subject, is about following the vascular and neuronal changes after targeted irradiation on the brain with using a gamma knife. So, hi, Olivia.
Hi, good morning.
Good morning. So can you introduce yourself and your work?
Sure. My name is Olivia Kelada. I just finished my PhD, a collaborative project between the German Cancer Research Center at the University of Heidelberg and Yale University in the US. I was looking at F-MISO PET imaging in animal studies and correlating that with partial oxygen pressure measurements, and then looking at the role of tumor hypoxia within the SBRT paradigm in clinical subjects with patients treated with SBRT with non-small cell lung cancer.
Okay. You presented a hypofractionation last Friday on the SIT workshop. Could you give us a short summary of your presentation?
Sure, without my slides, great.
No, just that, you know, for people that didn't see it.
Absolutely. So essentially, assuming the point of the talk was to briefly introduce radiation therapy and all the different methods we have and how we've gone from 2D conformal all the way to SBRT and eventually protons, but Professor Paganetti presented the protons, so I just left them out. He's definitely the expert in that. So essentially, the point I was trying to get across and what I hope people took home was, you know, what happens in tumors in patients who are treated with high doses in the case of SBRT, so 3 fractions of 18 gray, a 54 gray total dose. What does tumor hypoxia matter? Is it doing anything? Is it making local control worse or better? So the modeling tells us, using classic linear quadratic model, that actually at smaller doses, or at smaller fractions, higher doses, that the hypoxia has makes more of a difference. So you get more tumor cells that survive after those large few doses, so say 1 or 2 or 3 or 5 large doses. So we tried to look just simply what is the hypoxic fraction doing. So first we had to quantify it, which sounds easy when you say it in a sentence. It's very different in reality. So we did F-MISO PET imaging, mainly because that is the most used for clinical subjects. And we imaged on, let's say the schedule is Monday, Wednesday, Friday. So we tried to mimic that with the imaging. So on Monday, we did a F-MISO PET scan, and then in the afternoon, we irradiated with 18 gray. That Wednesday, another scan, and on Friday, the same. And the scans were done dynamically. So what that means is the patient is on the bed, and you are imaging for a whole 2 hours. Patient comes off for 30 minutes, you image for another 30 minutes, comes off again, and then for the final 30 minutes. So essentially you get 4 hours of data, which is great. And mainly because the F-MISO takes a while to get into the tumor and to clear, and you want to make sure it has time to bind to give you the hypoxic region. So long story short, in the patients that had a hypoxic fraction at baseline, not everybody does, and who finished the clinical protocol, the imaging protocol, we saw an increase in the hypoxic fraction on the Wednesday. So 24 to 48 hours after the irradiation. So that is, from the in vivo studies, some are the same and some are different, and I think it really depends on what time point you're looking at. If you looked at 6 hours, if that was possible, that would have been a very different result. So there's a number of theories for that. You know, maybe it's some endothelial apoptotic response. Maybe it's not, and the Kirsch paper and the Kolesnik paper would argue both sides. So it could also be that at these high doses, when we're escalating, there could be something happening with the biology and we just don't see it because the dose is so high. So that was to give you a summary. And the point and what we hope to do is, well, maybe the hypoxia, especially if it's increasing, maybe we should change the schedule. So if I was the clinical, radiation oncologist deciding the schedule, maybe it's better to wait a week. Treat on Monday, treat the following Monday. Allow the vascular response or whatever is going on at the high doses to resolve itself. As I said earlier, in conventional fractionation, you're allowing for oxygenation, and in hypofractionation, you're not. So maybe we need to give it a little bit of time to stabilize, and then, or we can take advantage of it. Give a radiosensitizer, or and capitalize or exploit this high fraction of hypoxia on day 2. But we'll see. I mean, that was in 6 patients, so really preliminary, really at the beginning.
Yes, and it's difficult because they have their own microenvironments around the tumors.
Absolutely, and they're not all the same.
Yes, exactly.
And that was, I think, after working with animals, that's the biggest shock, where you think, why aren't you all the same? And why don't you do what I tell you? So yeah, patient heterogeneity.
Yeah, sure. With the new generation of gamma knife icon, including the cone beam CT, we will have the capacity to detect and measure position changes, and the dose planning will be automatically adapted, which will be, I think, the major change, major improvement. Could you also explain us the great benefit for hypofractionation treatment with that kind of treatment, the irradiator?
I mean, onboard imaging is crucial, and we've known that for a long time. In the case of SBRT, in the case of hypofractionation or stereotactic radiosurgery, even more important because we're delivering such high doses. Same in the proton paradigm as well, right? So if I'm going to give you 18 gray, I need to make sure it's in the right place.
Yes.
And one way we've done that with lung, with the 4D CT, is take a 4D CT and look at the entire breathing cycle, and then make sure that your planning target volume is encompassing every gate. So you can have 3 gates or 10 gates, or in general we did 8 or 10, and then you make sure you have everything from end expiration to end inhalation, so that you are treating the whole volume during the treatment and you're not missing any part. So yeah, with the advent of the technology and the improvements, I presume we're just going to get better, and that's one of the things. It does is SPRT so successful because of the technology? Yeah, we're able to deliver a really high dose to a very small volume. And I think with technology, we will just get better at that. So right now, in lung anyway, we do T1 and T2 tumors, so small. Because the dose we can't increase the volume and risk the normal tissues. But maybe with the advent of technology, we'll get better at that. Maybe if we consider the hypoxic fraction, we'll be able to be better. And including, we normally do, so the RTOG 0236 trial that Timmerman put out with 55 patients, they looked at peripheral lung tumors because the centrally located ones had higher percentage of grade 3 to 5 toxicities. So maybe with the technology, maybe including information about the hypoxic fraction or other tumor microenvironment information or details, we can target it to those tumors as well. Because as you know, the lung patients before, they're inoperable. So they weren't candidates for surgery. They were getting some, very basic radiation, but in general, something palliative, and that was it. And now they have local control rates at 3 years of 97.3%. So that's, a drastic change. And I think especially with imaging and these new machines, they always have issues at the beginning. We should be able to improve on that. So that's going to be exciting, definitely, especially in lung patients and the other tumors of the abdominal area, pancreas, kidney, where local control isn't that good and hasn't been for a very long time.
Yeah, and you raised a very good point too, that we need an improvement on imaging system, because I am working with a radio-oncologist, and she's always scared about, not scared, but sometimes she has doubt about, is it a necrosis or tumor recurrence in the brain, and we can see with an efficient imaging tool. So I think we are in a good position with all the irradiation system, proton therapy, and even if we have to improve the treatment planning, but also we need to see better the tumors, and so it's really great that you made the MISO PET. So what are the future directions for hyperfractionation and its validation in clinical routine?
That's a good question. I think, what we've done, certainly, and I will speak about SBRT and lung and our experience at Yale. I mean, essentially every year, I can't remember what year that bar chart started at, maybe 2007. We've increased the number of patients being treated with SBRT. It's becoming standard of care. And as we get better and more accurate, and maybe we can treat more centrally located tumors, or maybe we can consider some other aspect other than there is a tumor and it's in this place and the surrounding normal tissue is that, I presume we will use it more. As far as the future, I think it's going to be really interesting as more people look at various aspects. I use tumor hypoxia as the example. So personalizing the SBRT treatments and really investigating what is happening in the SBRT paradigm. I mean, it's a very hot topic right now, and I hope it continues to be until we have more information. Whether there's some unique biological thing happening or not. So, yeah, is it going to be used more in the clinic? I presume. Yes. And I hope that as it's used more, we know more about how what the fractionation schedule should be. Not the size, but the timing.
Yes.
So,
sure.
And can we capitalize on that, as I said before, with sensitizers or cytotoxins or something?
Yes.
So, but that will take a lot more patients and a lot more trials. So I hope everyone has money to do that.
So to finish, what is your next scientific professional move?
Oh, okay. So I just submitted my PhD, and I will be going to work at Dana-Farber, Harvard up in Boston, to look within the SBRT paradigm with the Rebecca lab, the role, what we can do with nanoparticles. Can we, as I was saying, can we exploit something? Or I don't know what the result is going to be, but I think that's going to be interesting. We have to figure out how exactly we want to quantify or look at hypoxia in this paradigm, or a vascular response. But the plan will be to do that in animals with SBRT, looking at some aspect of the tumor microenvironment and the vasculature, and with the addition of golden nanoparticles. So I think it's going to be really interesting experiments.
Oh, yes.
But yeah, I have no predictions how it's going to go. Probably poorly at the beginning, and then we figure out the methodology. We'll find out some answers. So maybe next year, next RadRes, I'll be able to shed some light on our experience.
Great. Thank you. Thank you very much.
Thanks very much.